So at this point, we're ready to begin our regression model. Our data are uploaded. This is the view we left you in. We're going to be doing kind of a rudimentary regression because creating a good regression model actually takes a lot of experience, and it's a little bit of an art as well as a science. So we're going to do just a basic model, and we're going to just remember that we haven't even checked the assumptions because this app that we're using doesn't allow us to do that easily. That's kind of one of the drawbacks of using a free service like this, but it still gives us a feel for it. So let's go for it. You'll recall that in PSPP, we have a variable view, which we're in now, where we can change the characteristics of the variables, and a data view by clicking on these tabs at the bottom. Either way, you should have the same menu at the top. So we're going to go to Analyze and all the way down to Regression. And we're going to select Linear Regression. And I'm going to reset it here because I'd already done something with this. So academic performance is what we're measuring, what we're predicting. So we're going to put that in our dependent box. And we'll take all of these predictors, just these factors that we think might predict academic performance. We won't include random or student ID, and let's put those in the independent box. We won't change any of the settings. We're just going to click OK. And this is the output that we'll get. I'm going to talk you through it a little bit. It's also in the slides, so I'll just address it briefly here. We'll recall that the R square is the explanatory power of the model, and that the model is adjusted slightly to account for the number of variables that have been entered. And typically, the adjusted R square goes down with more variables. 0.58 is acceptable, and you'll recall the thresholds from the lecture. The ANOVA is the statistical test that we use. And just to orient you through to these terms on the left menu, these are exactly what we calculated when we did SS total and SS error. So SS total is just the sum of squares for the Y variable. That's it. It's just the deviation, the squared deviation, sum of squares. The residual, the sum of squares for residual, is just the SS error, which is Y minus Y hat, or if you want to picture in your mind's eye, it's like the distance between each score that was predicted and the actual score on that little scatter plot. And then the regression is the difference between the two. If you take the total and subtract the residual or the error, you'll get this regression. And that is the difference between the predicted Y value, Y hat, and the mean. And so we calculate the ratio just as we did in the bivariate correlation. We compare it on that F ratio distribution, the same as we did when we did ANOVA in Chapter 9. And you can see here that our model is significant. Whenever you see this SIG, that means how significant is the model, and you know the thresholds we typically test at, 0.05, 0.01. This is considerably lower than that, so it's a very significant model. Finally, down here we have our beta weights for each predictor. You can see them listed here. And I keep saying beta, but remember the beta is the standardized coefficient that would be appropriate to use if we were using z-scores. The unstandardized coefficient is what we use when we're actually applying a model to data to predict an outcome. And the constant in this case is the A in our predictive model. And each of these numbers right here under B relate to those B weights that we multiply times each person's score to get a final outcome. We can see that t-tests are conducted within this framework to determine which of these predictors are significant. And in this instance, we have significant predictor for anxiety. As anxiety goes down, we have a negative sign there. As it goes down, academic performance goes up. Self-esteem, we have a not significant predictor with a significance level of 0.376. So it doesn't meet statistical significance. And likewise, depression. It does, as it goes down, performance goes up, but it's not a significant predictor, which is interesting. All the remaining three are significant as social problems go down. academic performance goes up. As health problems go down, academic performance goes up. And as living situation goes down, academic performance goes up. Excuse me. As living situation improves, academic performance improves. I hope you'll forgive me. This is about the 8th time I've made this video, and I feel a little bit tongue-tied at this point. So when we have something like this, where we know that depression and self-esteem really should both contribute to this model, it's possible we have some kind of a confound. And because of my familiarity with the data, I am wondering if social problems are kind of taking away the predictive power of both self-esteem and depression. And so even though we probably will keep this model, I'm going to go back to my data and run one more regression. I haven't actually done this one yet, but I'm going to go ahead and do another linear regression. And I'm just going to pull these social problems out of there and just see what happens when I remove it from the model. What I'm looking for in particular is that adjusted R squared. I want to see if it decreases or stays the same or increases. Not sure why that's not sure why everything seems to be so magnified on my screen here. Let me grab this output again. Here we go. So it looks like when we remove social problems, the adjusted R square goes down, but depression does become a significant inverse predictor. We also get closer to significance for self-esteem. But it does seem like maybe measuring it in terms of social problems is the best way to go. I also wondered whether self-esteem was sort of overriding depression in terms of being a predictor in the model. But for the sake of this class, I'm just going to go ahead and use all of these original predictors, even including these 2 non-significant predictors. If we removed them and the model improved, we wouldn't want to include them. But if we remove them and the model diminishes, then we want to include them. Those are all the ones, earlier versions I did. Not sure why this is showing up on the wrong screen. Okay, so just pulling that up, I'll show you what I mean briefly. Let's just run this model one more time, and let's use a linear regression, and let's just pull out, let's see, self-esteem was non-significant. Let's see what happens when we pull self-esteem. We're looking at that adjusted R squared again. And so here's our output. So we still have that adjusted R squared of 0.47, more than half the variance explained, which is really good. Now, all of these are significant, including depression. So it's kind of interesting, as you pull out the overlap between depression and self-esteem, we end up having depression become significant. But I still think in this case, we're going to leave all these predictors in. So what we're going to do for the next part of the problem is to just pull these predictors, put them into the spreadsheet, and eventually use them to test the model. So that will be the end of this video, and we'll continue on with the next one.